Pluto is a distant and confusing smaller planet that was once an individual member of our planetary system's family. However, recent astonishing statements by leading astrophysicists Neil deGrasse Tyson and MIT's Michio Kaku have brought Pluto back into the spotlight with a shocking revelation. They suggested that this cold world is on an expected collision course with Neptune. Yet, how could this occur, and what might be the consequences of such a gigantic event? Are we witnessing an unexpected cosmic peculiarity, or is there something more to this approaching divine crash? Join us as we investigate the possible outcomes of a Pluto-Neptune collision. Pluto, a former planet that was downgraded to a dwarf planet, remains a subject of interest and study in the cosmic community. According to recent forecasts by leading scientists, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potentially risky impact between these two planets, which could pose a critical risk to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our solar system. It takes a stunning 248 years to complete a single orbit, meaning that since its discovery in 1930, it hasn't even completed one full revolution yet. The intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the near-round orbits of the major planets. What makes Pluto's orbit even more curious is its inclination, measured at 17 degrees to the ecliptic plane. The way Pluto follows its orbit is considerably more extreme compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its crossing point with Neptune's orbit. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, defying what we might expect based on their positions in the planetary system. This leads to the natural question: why hasn't Pluto crashed into Neptune? The answer lies in the gravitational effects of other planets. The investigation of Pluto's orbit began shortly after its discovery. Initially, astronomers tried to determine its unusual path. Unlike other planets, whose orbits lie mostly near the ecliptic plane, Pluto's orbit is significantly inclined and elongated. The mystery deepened with the realization that Pluto's orbit does, indeed, cross Neptune's. The stability of Pluto's orbit, despite these complexities, is proof of the intricate mechanics of space. The three-body problem in space involves understanding how three objects, such as Pluto, Neptune, and the Sun, move and interact with each other due to gravity. It's like predicting their movements based on their starting positions and gravitational pulls. In Pluto's case, this problem shows how its orbit, Neptune's orbit, and the Sun's gravity work together in a complex way. The terms alpha libration and degree libration, along with the VZK oscillation, are key to solving this puzzle. According to astrophysicists, what keeps all planets in their orbits is a phenomenon called alpha libration. In the case of Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, it is found no less than 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from intersecting. Extension libration, on the other hand, refers to the vertical movement of a body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned completely above their orbital plane, offering an additional layer of protection from potential impacts. Another important factor in this situation is the VZK oscillation, named after scientists Bond, Zippel, Leo, and Kai, who studied how objects move in space. It describes how three space objects, like Pluto, Neptune, and the Sun, interact gravitationally, influencing their movement. In Pluto's case, the VZK oscillation helps explain why its orbit around the Sun is so unusual. Despite its seemingly erratic path, this oscillation helps keep Pluto moving smoothly for billions of years. The VZK oscillation demonstrates that, even though space may seem chaotic, some patterns and forces maintain stability. These factors help sustain Pluto's orbit, ensuring it doesn't crash into Neptune or lose its way. This three-body problem is fundamental for understanding how orbits change due to gravitational influences. Mathematical simulations from the late 1980s revealed that, despite these stabilizing properties, Pluto's orbit is actually chaotic. Slight deviations in initial conditions can lead to massive changes over time. However, these unusual properties of Pluto's orbit have been found to maintain stability over very long time scales, effectively keeping chaos in check. Recent computer models have helped us understand how giant planets like Neptune, Jupiter, and Saturn influence Pluto's path around the Sun. Neptune has a special relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune finishes 3. This resonance helps stabilize Pluto's orbit. But Neptune isn't the only factor. Jupiter's gravity also plays a major role in shielding Pluto's orbit, and Saturn contributes as well. Studies show that Jupiter's gravity alone is powerful enough to ensure Pluto remains on a stable path for billions of years. These peculiarities are essential in the larger context of the universe. Without these mechanisms, the solar system would be a much more chaotic place, with celestial bodies possibly crashing into each other or being ejected from stable orbits, leading to cascading effects on other objects. Understanding Pluto's orbit is crucial, especially in discussions about its potential collision with Neptune. This gives us a clearer picture of the solar system's dynamic nature. Pluto exemplifies how even the most seemingly unstable orbits can reach equilibrium through the intricate interaction of gravitational forces and orbital mechanics. Studying Pluto raises philosophical questions about order in cosmology. The decision to reclassify Pluto as a dwarf planet in 2006 sparked debates about what defines a planet. The global astronomical community's definition focused on criteria such as orbital dominance and size, leaving many to question the implications of such classifications. Moreover, the potential for future exploration of Pluto and the Kuiper Belt remains an exciting frontier. Advances in technology and mission planning may lead to additional spacecraft being sent to study Pluto and other distant objects. Such missions could provide valuable information about the primordial materials that formed our solar system, possibly shedding light on the origins of life on Earth. Pluto remains a symbol of the never-ending quest for knowledge about our universe, inviting scientists and enthusiasts alike to explore the mysteries that lie beyond our earthly bounds.